So today we're going to move into chapter 6, and part of chapter 6, it talks about interval notation and inequality notation. So I want to kind of mention that first. Of course, this here would be an inequality. X is greater or equal to 3. If I draw this on the number line, what I can do is put the critical point of 3 here. And then to be greater or equal to 3, what we do is we use a solid dot, and we would shade to the right of 3. Now, interval notation has this left bound, right bound stuff. So the left bound would be this 3. And since it's included, we would use a bracket to start with the 3. And then the interval continues to the right forever. So this will be to what's called infinity. And we would use a parenthesis there since parenthesis is unbounded. So if I have x is less than 7, if I just put 7 on the number line, less than 7 means we do not include the 7, and we would shade to the left of 7. So the left bound would be negative infinity, and we would not include it. We use a parenthesis. And the 7 is not included either, so we'd use an open parenthesis there as well for that. So again, parentheses are to exclude, and brackets are to include the endpoints. If I have -4 to 4, so my left bound is -4 to 4, notice that neither one of these are included. So when I use interval notation, we use parentheses for that. -4 to 4 would be the interval notation for that. If we have 12.5 to 15.6, again, the 12.5 would be my left bound. The 15.6 would be my right bound. And again, neither one of them is included. So we'd be using parentheses in that situation. So 12.5 to 15.6. It kind of looks like an order pair, but this is actually called interval notation. So you just have to pay attention to context, because some things can look the same. So in chapter 6, we know we're getting into what we call confidence intervals for the mean. So we're talking about these confidence intervals. You know, how good do you feel about something? So one of the things is there's what's called this point estimate. A point estimate is a single value estimate for a population parameter. The most unbiased point estimate for a population mean is going to be the sample mean. So if I have a bunch of hours, let's see what this refers to here. A researcher is collecting data about college athletics conferences and its student athletes. A random sample of 40 students is selected, and their numbers of hours spent on required athletic activities for 1 week are recorded. So find a point estimate for the population mean. The mean number of hours spent on required athletic activities by all students in the conference. So to find a point estimate, basically what you're saying is about, on average, how many hours does a student athlete work? So that's kind of called a point estimate. So in other words, we're just talking about the mean. So to do the mean, you would actually have to add all the numbers up and divide by the number of numbers. So remember, the sample mean is actually going to be the sum of the data divided by the number of pieces of data. Now, instead of doing all that, we can input this into our calculator. So remember our little calculator here. So remember, if we went to stats, you could edit, and I've already put my data in. And remember, to do the calculations, you hit stat again, and you go over to calculate one variable statistics, and the frequency list should be empty. So you should just have list 1 listed there. If you have a frequency list, you need to delete that. We don't have one this time. We just have one list here. So that's how our x bar is going to be our mean, which would be 21.05. So that would be a good estimate of about how many hours a student athlete is working in 1 week. So we have what's called a point estimate. But now if you were thinking about, if you picked a specific athlete, do you think that athlete would have worked exactly 21.05 hours? Chances are that's not going to be exactly true. So this is only an estimate of all the athletes. And again, we're using this mean here to actually represent the population. And again, we can do that since we do have a random sample of 40 student athletes. Remember, 30 is kind of the magic number for a lot of things to be what we call later on normal distribution that we'll get into. So next thing we have is what's called the level of confidence, or also the margin of error. So sometimes it's also called the maximum error or of estimate or error tolerance. So it's going to be the greatest possible distance between a point estimate and the value of the parameter it is estimating. For a population mean, mu, where sigma is known, the margin of error is going to be given by this formula. So what's nice here is in this section here, they're going to give us the standard deviation. So we have this formula where E stands for the margin of error, and the ZC stands for our Z-score that we'll need. And sigma X bar represents the standard deviation of the means, which they can then kind of modify to this formula here. So it's going to be a Z-score divided by the standard deviation divided by the square root of the sample size. So remember, to use this formula, if we're talking about normal distribution, our sample size has to be greater than or equal to 30. So we have to have that involved here as well. So level of confidence, the most common ones you're going to be seeing is like 90%, 95%, and 99% confidence. These are the Z-scores that go with it. So again, I could use my calculator, and remember, I go to like second distribution, and notice number 3 is where you found your Z-scores. So, to find the area of the curve, notice that, 90% would be this middle part. But remember, the area we're talking about is actually to the left of that. So if this is 90%, we know that this is 5% here and 5% there. So we'd actually have to use 0.05 for the area of the curve. And then everything else can stay the same. So move on down to, notice how we get this negative 1.644 or 645 if we round it to the thousandths place. 95% confidence level, 95% means there's 5% left over on each side, which means that would be like, 2.5%. So if I use my inverse normal distribution, I can find my Z-score, number 3. But if it says 95%, notice that we have to have like 5% on each side, but that actually leaves me 2.5%, or in other words, 0.025 would be that value. And then if we move on down here to paste, notice how we get this negative 1.96, notice at 95% confidence. So these Z-scores, if you just kind of jot them down, they're going to be used quite a bit. So we don't have to go back here and do this inverse norm each time for these confidences. We can just take advantage of that. 99%, notice that there'd be 1% left over. So it's 0.01. But I would actually have to use half of that. Half of 0.01 would be like 0.005. So that'd actually have to be 0.005 under the curve. That'd be this itsy bitsy part over here. And if we move on down to the paste, it should give us this, negative 2.57. But again, we are also can do this to the right as well, since we really don't need negative values here. We just need these Z-scores as positive values. So remember that the symmetry kind of kicks out the ones to the right as well. And we're going to use the ones to the right. These would actually be negative Z-scores, and we want to use a positive Z-score for that. And the symmetry allows us to do that. So if I want to look at this example here, use the data in example 1 and a 95% confidence level to find the margin of error for the mean number of hours spent on the required athletic activities by all student athletes in the conference. Assume the population standard deviation is given. Now notice in our calculator, if I look at this stats and go back to calculate, it gives us sigma is 2.4. So it does give us a standard deviation there. But also here it's 2.3. Keep that in mind that we're still only using a sample, not the actual population. So that's not actually true. If 40 was all the population, then that's fine. But remember, 40 is our sample, so we can't actually use that 2.3 in our that 2.4 in our data, because the 40 is actually a sample population. So if I was looking at my calculator, I should be using the sample one, which is the 2.4438 one. So keep in mind, we don't have a population, we have a sample of the population. So we have that going on there. So anyway, to find the margin of error, we have this. The margin of error can be found by multiplying the z-score times the standard deviation divided by the square root of n. So the margin of error, which we use E for that, is going to be the z-score times the standard deviation divided by the square root of n. So 95% confidence, notice how we can actually just go up here and use our shortcut, which would be 1.96 is going to be our value here, our z-score. Our standard deviation was given to us. That's going to be this 2.3. And we're going to be divided by the square root of n. So I think we had 40 was our population in our sample. We had 40 students here. So our sample population was going to be the square root of 40. So if I can slide this over, I can actually find my margin of error. So if I quit that and go then, 1.96 times then, that's not 1.96, 1.96 times then 2.3 divided by the square root of 40. A lot of times I'll put fractions in parentheses. So that kind of helps me out there. Hit enter. You also could use, you can go 1.96 times, and then again, I didn't hit 1.96. I get times, and you also have the fraction button, which is above the, I think you use the alpha key and hit F1, and number 1 is a fraction one. So you can actually type it in that way as, 2.3 over the square root of 40. If you hit enter there, it should give you the same value there. So if you get confused, there's also the alpha F1, which gives you the fraction menu. So again, our margin of error, a lot of times looks like they round these to, looks like the 10th place a lot of times maybe. So we'll say 0.7 would be our margin of error. We round to the 10th place. Hopefully they'll tell us how to round. But so we have that kind of going on there. That's how we determine what's called a margin of error. Another thing is constructing a confidence interval. Notice there's this word interval here. So an interval is going to be either an inequality or interval notation. So what happens is, we start with that point, which was that mean up here. The mean we said was 21.05. So that would be our, if I was trying to draw a number line, help us out there a little bit. Let's see if I can do that. So instead of trying to draw all that normal distribution, we'll just kind of keep it a little bit simpler. So to do a confidence interval, we have our mean, which is going to be the 21.05. And to do an interval, what we did is we add and subtract the margin of error from the mean to get our interval. So this is what this is kind of saying is, so first off is the standard deviation has to be known. The population has to also be normally distributed, or the sample size has got to be greater than 30. So we passed that test. So we need to find the mean for the sample, which we did. That's X bar. So the critical value, Z, we actually are going to skip that and go straight to our shortcut because we have those Z-scores in our table as well. Find the margin of error, which we just did. And then what you do is from the mean, we subtract the margin of error and add the margin of error to get the left endpoint and right endpoint. So the left endpoint is going to be 21.05 minus 0.7. And the right endpoint is going to be 21.05 plus 0.7. So subtraction is not as easy, so I'm going to go ahead and just use the calculator for that. 21.05 minus 0.7. That's going to give me 20.35. And then 21.05 plus 0.7, that's just going to be 21.75. So what we have then is our interval would be 20.35 over to 21.75. And since we don't include the endpoints, we can use parentheses there or open circles, and that would be our interval. So if I'm using an inequality, we would say 20.35, and again, I don't know if they use X or what there. I think it's probably from the mean. So the mean was in the middle. Let's see. So 21.75. Or we can just write as an interval would be 20.35 to 21.75 would be our interval of confidence. So basically, we're 95% confident that the study hours for those student athletes should be between 20.35 and 21.75 hours. So that's and again, we're talking for the population, and that is in that sense as well. So keep that in mind. Let's see what else we have here. All right, we'll stop there.